Hello everyone, I'm Lan Duan, a PhD student from Hong Kong Polytechnic University. I will present our paper, Online Recommendation-Based Convolutional Feature for Scale Video Visual Tracking. Before going to the details of this paper, I would like to briefly discuss the motivation of this work. Onboard visual tracking is a fundamental task for many UAV applications. For instance, the inspection of survivors or urban facilities, package delivery, and dynamic obstacle avoidance. Those tasks require the UAV to keep looking at the target and track their locations. In the past few years, vision intelligence has achieved significant progress fueled by the deep learning method. However, the progress becomes much slower in UAV applications due to the limitation of the hardware platform. The drones has to process many tasks concurrently, such as navigation, target detection, tracking, path planning, you name it. Unfortunately, the powerful GPU usually is not a feasible option for small UAV or MAVs. With limited computational resources, we need to optimize the onboard system. In this paper, we aim to use only a few layers of a backbone CNN to perform predefined or undefined target tracking. We know that the backbone CNN is acting as an unsupervised image feature extractor, so we need the regression layers to recognize a large number of objects. But visual tracking does not require the classification process. Moreover, the target may not be included in the training dataset. We present a method to automatically select the CNN features to rebuild the target model efficiently for visual tracking. This allows the UAV to save more time to process other tasks, such as path planning. The image feature can also be used for the loop closure process in the navigation module. This is an illustration of the basic idea of this paper. We use VGG19 as a backbone CNN. The feature of the tracking target extracted from different layers are given in the first row. When layer goes deeper, the semantic level of the feature becomes higher, but we also lose the location information, so low-layer features should also be used for tracking. Dr. Thomas' work, HCF, given the right side, using a similar idea to perform visual tracking. In their work, however, they use a fixed layer and all feature maps of those layers to rebuild the target model. We argue that different target has different semantic level. For a simple target, we can use only a few layers to represent the target properly. And not all feature maps are necessary, as some of them are background features. Here we present a CNN feature recommendation approach. Denote foreground region F, the background region B, and feature map X, respectively. The recommendation score of X is given by dt times gt, where the dt and the gt are the distinctive term and gain term, respectively. The di is the pixel distance between ith pixel to the target center, and r is the diagonal length of the region F. As the figure shows, the peak activation with a large distribution is designed to result in a low score, because this means the feature is not a discriminative one. dt provides a convergent nonlinear weight distribution, referring to the term T, which labels foreground and background by the positive and negative scores. gt, on the other hand, amplifies the discriminative score by comparing the power of foreground and background. F bar and B bar are the mean value of F and B, respectively. So, when dt score measures the feature quantity, gt measures the statistical difference between foreground and background. After we score all feature maps, the score of layers are also obtained by the sum of the feature map scores. Hence, we could rank the layer and the feature map in each layer. The target model will be rebuilt from the weighted sum of top m feature maps in the top n layers. It is noted that due to the pooling process, all feature maps has to reshift to a fixed size in order to sum them up. This is an illustration of the performance of the recommender. we use UnoV3 to detect an aircraft which runs at average 40 FPS on GPU 1080 Ti. Once the aircraft is detected, we use the proposed recommender to select the top 1 layer and the top M features in this layer. By the proposed method, the best layer is 14, while there are 106 layers in the UnoV3 in total. We visualize the mean activation of this layer. In contrast, we show the weighted sum of the same layer. The result indicates that the proposed method has selected the target feature properly. Then we start tracking the peaks of the target features. During tracking, we use the pre-selected layer and feature maps. We can find that the output could always represent the target. Indeed, for a complex background, the output may not be such clean, but we can focus on a small target region. The distribution of the activation peaks can also be used for the scale adaptation. In order to perform a robust and accurate tracking, we introduce the correlation filter. The tracking pipeline is given in the figure. When initializing the tracker, we use a target model to train a correlation filter. In each new frame, we extract the candidate model from the same recommended CNN features and relocate the target using correlation filter. In addition, the correlation filter and scale will be updated. The standard process of a correlation filter is simple. We have a regression problem where the X is a target model, Y is the desired output, which is a Gaussian peak that represents the target center location. Normally, it is faster to compute the Fourier domain. The closed form solution and the filter updating process are given here. To update the scale, we present a special temporal-based mean channel method. The idea of the mean channel is to find the statistical variation of the target feature distribution over continuous frames. All activation peaks within a frame buffer will be projected onto a current target through a mean channel, which is a binary target mask. The final scale variation is computed by the ratio of the statistical parameter and filtered by median filter, where the mu and sigma is computed by a weighted standard deviation. In offered testing, we implemented the proposed method on VGG19. The tracking accuracy and robustness is evaluated on the visual tracking benchmark. The result demonstrates that the proposed tracker achieves competitive performance in the state-of-the-art. We also performed the proposed track on the dataset recorded by a rescue drone to track the survivors and their belongings. The onboard view suffers from a low frame rate, aggressive motion, illumination variation, and image blur. The result demonstrates that the proposed method could track the untrained target properly in terms of the accuracy, scale adaptation, and robustness. For onboard tracking, we implemented the proposed method on UnoV3. The UAV was flying under Vicon environment. The task of the UAV is to perform the traffic light inspection in full autonomous. As you can see, the unit detection runs on average 4 FPS. The FPS rise up to average 17 when switched to the tracking model. Thus, the UAV got extra computational power to plan the path and process data analysis. For untrained target, we can manually select the target and the proposed tracker will learn its feature online. We have also developed other models such as visual odometry and map exploring tools. In future, we will integrate those models to enable the full autonomous flight for UAV. You are welcome to check our GitHubs, which are given in this slide. Thank you very much.